All right, today's seminar in the group meeting is by Thales Rick Perche, and he's going to tell us about particle detectors and antiparticle detectors. And I can already tell that aesthetically speaking, probably this is one of the top talks that we've ever had. So let's go.
Well, let's hope that the content also is fair to the aesthetics. Well, thanks for the introduction, I do. And well, as you mentioned, I'll be talking about particle detectors here, and this sort of concept that arose in a paper by Bruno, Landulfo, Matzos, and I. That is the concept of antiparticle detectors. There we considered a particle detector that was able to probe the neutrino field, essentially, or the antineutrinos via the inverse beta decay. I'm going to talk a little bit more about this later in the talk. But before, I want to give a brief introduction about particle detectors. And this is current work that I'm doing with Eduardo. And hopefully we'll be able to finish reviewing the sketch that we have of the paper, and we'll be able to post it on arXiv and then submit it somewhere soon enough. So this talk is organized as follows. First of all, I'm going to give a brief summary of the light-matter interaction. This is something that most people here in the group are already very familiar with, so I'll try to just go through it. And you will see that lots of the examples that I will be solving here will be very related to the things that Ericsson, Edu, Irene, and Alison worked on, and Ericsson presented here. I'll put the citations whenever they actually show up, of course. But yeah, so I will start by talking about the light-matter interaction and try to sort of introduce the UDW model as both a way to detect particles of a massive field, but at the same time to try to just see what are the features of the electromagnetic of the light-matter interaction that are not grasped by the UDW model, and also the ones that are. So just a brief comparison. So the idea is essentially to see how we can use the UDW model to try to simplify this light-matter interaction to a simpler particle detector model. Then I'll introduce the Beta Decay model, which is this fermionic particle detector that was introduced in the paper that I mentioned previously. And then the goal, the final goal of this talk will be to sort of try to find a model of particle detector that will be able to simplify and simulate the effects of this particle detector model, but that's simpler, right? Essentially, we'll be looking for a model that will couple to a complex field. I'll be calling this the complex UDW model. You can call it the anti-UDW model. It still doesn't have a name. I mean, it's something that is very recent, such as the Beta Decay model, which also can be called, I don't know, neutrino model, fermionic model, whatever. And at the very end, I'll just have a final slide to conclude what are the features that we can actually expect this simpler model to grasp from this Beta Decay model. So first of all, let's talk about the light-matter interaction. The idea is to essentially describe an atom interacting with an external electromagnetic field, right? And to do this, in order to do that, of course, we need to describe the atom, we need to describe the electromagnetic field, and we need to provide interaction between both of them, and somehow try to come up with a particle detector model. That is, we have to factor some localized system that is non-relativistic or first quantized, and that interacts with the external electromagnetic field. So we start by describing the atom, right? I'll just use the simplest possible description here for a hydrogen atom. So the Hamiltonian would just be the electron around a central charge, around a proton, if you will. And of course, this is a calculation we've all done in our lives. We know that we can find a discrete part of the spectrum for this Hamiltonian, and we can find the wave functions associated to this. And the energy levels are given by essentially the fundamental energy of the hydrogen atom, all of them divided by this n squared. They're all negative, and well, that's what will actually matter for this review. So the external electromagnetic field will be given by, I'll just expand it in terms of plane waves and the polarization vector, right? So this will be the expression that I'll be using later. I'll actually generalize this for a general expansion, but for the purpose of showing some general features of this model. But you can think for every purpose that we're just expanding this. This is all very straightforward. And the interaction between them, I'll prescribe it as the dipole interaction. So there are this is not 100% precise. There are some approximations involved. The dipole approximation, that this has been very well studied in well, numerous papers. I have cited two of them here. So this one of Richard and Edu, where they consider the center of mass, degree of freedom to actually also play a role here. And this one from Nico, Jorma, and Edu regarding the difference between the P and A, which sort of arises more naturally out of the minimal coupling, and this D.A. But for every purpose, for our purposes, we would just consider this to be the interaction between the hydrogen atom and an external electromagnetic field. So you can imagine that, well, this is the standard interaction between a dipole and an electric field. The only thing is that...
sorry, Thomas.
Yeah, sure, Richard.
You have 1 over mass in there.
This... Yeah, the 1 over mass shows up in the P.A. It doesn't show up here. Thank you for that, Richard.
Yeah,
there's a typo. Yeah, there's a typo. Yeah, thanks for that, Richard. Thanks for the catch. Yeah, there's a typo. And well, actually, this typo propagated throughout the whole thing. So yeah, thanks for that, Richard.
Everywhere. Yeah.
Yeah, but so m in this case is just a constant that is set to 1, and here m is just an index. Okay. And thanks for the catch, Richard. Well, yeah, so yeah, the thing is, this will be the interaction we're going to consider. And then this dipole is essentially the X operator, but I'll write it in terms of I'll write it in the interaction picture and in terms of the eigenbasis of function in terms of the basis of eigenfunctions of the free Hamiltonian, right? So if we do this, then what we get in the end is this dipole here, where this omega here is the energy difference, right? Right, we're in the interaction picture. And then if we want to further simplify this model, well, so first of all, at this stage, we already have this, particle detector model, right? We have this localized system, this atom, which couples to an external quantum field in this linear way, which is great. It's simple, and well, that's it. But if we want to further simplify this model, we can look for energy transitions between two fixed states, so like a ground state and an excited state. In this case, this dipole operator looks like this, okay? And essentially, this lambda of x would just be the product between the psi excited star and psi g, and here will be the conjugate, and this omega will be the energy difference between the excited and ground state. And in this case, the interaction Hamiltonian can be recast as this term here, as this integral over space of this Hamiltonian density, of the scalar Hamiltonian density, if you will. And again, this m here should be 1, as is noticed by Richard. Thanks again for that. And then we can see some features that will be present in every single particle detector model we will talk about in the future. So first we see a coupling constant, E, right, m equals 1. We see a space-time smearing vector in this case. So this is the vector that will actually define the dipole operator as a vector operator, and that will be, we'll take the dot product with the quantum electric field here. And here there is the detector gap, right? So these are three things that will be present in every particle detector model we'll see. And also, of course, we need the raising and lowering operator associated with the detector gap and the quantum field. But the things that define the detector essentially are these three quantities there. The smearing function, the space-time smearing function, or vector or spinor, we'll see different cases, the constant coupling constant, the coupling constant, and the detector gap. And if I want to actually get the excitation probability for this detector model, so the probability for the atoms to start in this ground state and to get excited to an excited state, here I have decided to write it in a covariant way. So it really doesn't change. This is only the scalar product between these, because this would be associated with the dipole of the atom. Thus, this is a space-like vector, and so is E. So everything here will be, this is just the dot product for every purpose. I just didn't want to write the tensor product between E and itself and then bracket it with vectors here. But so the excitation probability to first order in the coupling constant, so there should be an E squared here, right? The coupling constant, sorry for that. But it will be given by this expression here, which hopefully is familiar to most of you. So here we see the detector gap. the space-time smearing function, sort of regularizing the 2-point function of the field if the field's in the state psi, right? So if the field's in the state psi, we get this excitation probability for the detector. And in this presentation specifically, I'll be looking for something that has been looked in detail in Ericsson's paper, as I said, the paper from Ericsson, Irene, Alison, and Eduardo, which is I'll be trying to shoot a one-particle state at the detector, or to consider the detector to be probing a one-particle state, right? So a general one-particle state in this theory will be given by some over polarizations of a momentum distribution. And in this case, what happens is that the Weightman function of the field, the 2-point function for the field, it actually splits itself into 3 terms: the vacuum Weightman function plus 2 particle contributions, which are essentially given by this these functions here, which are essentially that they are. So UK of x here are the mode decompositions for the electromagnetic field. Epsilon mu are the polarizations. So essentially what's happening here is that we get these fx of f mu of x are sort of like the position representation of this function f with respect to the mode decomposition that we pick for our field, okay? And this will be a general feature that will show up in every detector model we'll see from now on, whenever we decide to consider a one-particle state. So yeah, keep that in mind. And what's interesting to notice here as well is the fact that you can, this UKs, they're the positive frequency modes, okay, in my convention, which means that they come, they're an integral, they come with an e to the minus I omega k t, right? So if you consider a detector or detector to be inertial, then these stalls here will simply be t in inertial plane wave mode decomposition, and the detector to be inertial. Then what's going to happen is that this will be an e to the minus I omega t, and this will be an e to the I omega t. So you can already see, for example, that this last term here, it will not contribute in the long time limit because we will pick up a delta of, oh, sorry, this last term here will contribute in the long time limit because we'll pick up a delta, which will be, after integrating over time, that will be of omega minus these omega k's for each k. But here, on this term here, because we have a star here, a conjugate, then this term here will actually come with a positive sign, and we'll pick up a delta of big omega minus omega k. So this guy will never contribute, and the vacuum excitation probability will always vanish in vacuum as well if the detector is inertial. So essentially what I'm trying to say here is that this term here can be regarded as a counter-rotating term, this is a co-rotating term, and this is the vacuum contribution. And both of these turn out to not contribute in the long time limit for an inertial detector, and only this particle content will actually be responsible for exciting the detector. So let's see this in a more specific example, right? So I'll consider an example where I pick the plane wave decomposition for the electromagnetic field, and I choose momentum profile functions f of k for the detector to be given by this these Gaussians centered at momentum k0 with a spread sigma. And so it's a Gaussian momentum space. And we have 2 polarizations. So I'll associate this vector alpha 1, alpha 2 associated to the, so alpha 1 is associated to the modes related to the first polarization, alpha 2 to the second, right? And the detector, it will be assumed to be point-like for this simple example. And I will then consider this atom to have this ideal dipole, essentially, in this direction x mu, where x mu is a space-like vector orthogonal to the trajectory. And given that I'll consider the detector to be inertial, then this trajectory will be, then this will just be a vector with 0 time component in these coordinates. And I will also take the long time limit so that this chi of t will end up just being 1 in this limit, right? So if we do this, then we get the following results for the probability. So first of all, what we have is a dipole here, and we're shooting not a wave, but a combination of electromagnetic waves essentially there, right? And to do the computations, you need to choose the polarization vectors for to describe the electromagnetic field. So I picked polarization vectors such that only the first one has components in the direction of this of the dipole of this ideal dipole of the atom, and the other one is orthogonal to it. So that's why in the probabilities you always see this alpha 1 squared, and there's no alpha 2 contribution. This means that only the particle states that are associated with the first polarization vector actually contribute to this excitation probability. And of course, the excitation probability will also depend on the relative angle between k0, the propagation vector, and the dipole operator. So in this plot here, I plotted the probability, the excitation probability divided by the coupling constant as a function of the angle theta between them. So as you can see, the contribution is maximized when theta is pi/2. So when the dipole of the when this ideal dipole is orthogonal to the propagation vector, and that's because this maximizes the value of the scalar product between D and E, because E is always orthogonal to the propagation. So in this case, E and D would be parallel, and then you get the maximum contribution. And as you start to bring this dipole vector down compared to k0, you see the probability decreasing. Of course, we see a resonance effect at omega equals the absolute value of k0, right? So we see that all of these probabilities have a peak when the detector gap is equal to the energy of the state, to the average energy of the state we're considering. And yeah, that's it. And essentially here are the full expressions for the cases of orthogonal and parallel, k0 and D. And these are not the same probabilities that we obtain for the scalar case, as we will see, right? And every single effect of resonance and the probability going to 0, sigma goes to 0, is also present here. But I'll talk more about these. So these are facts that Erickson talked about in his presentations, right? I'll talk about these later when I talk about the UDW model. So what is important to keep in mind here is that this excitation probability actually depends on the relative angle between this dipole and the propagation, and that it has this resonance effect at omega equals k0, right? The rest I'll comment more as we talk about the scalar case. So let's talk about the UDW model. So what I will call the UDW model, and this. So far, any questions regarding the electromagnetic one? Just before I start this next step.
So Thales, it's just a cosine factor, right, of the angle between the dipole and the electric field, isn't it?
No, it's
No?
really not. No, it's really not. It's a very complicated expression.
What is the angular dependence? Because
it's very complicated.
If it's not a cosine factor, I would be slightly doubting it, because in the Pothas paper we got a cosine factor square as that.
Yeah, but in that case you don't have an ideal dipole, right? And I believe a cosine squared factor would arise in that case. And actually the computations for the case where you consider a dipole associated to the actual oh yeah, by the way, did you consider one particle stays there? I don't know you did.
No, we didn't. But with the vacuum excitation, we got the cosine factor. It's different in the sense because we had the polarization vector of the in the interaction, right? When we do the analog to the analog, we pick a polarization direction, obviously. Mm-hmm. But yeah, in those cases, okay, it's more complicated.
But in this case, like the vacuum contribution is washed out, right? Because this is the long time element.
That's right.
So the dependence is on the relative angle of the dipole and the
it could be different, because in that case it's two atoms, right? And it's kind of the excitation of one and the other. So the assumption would be that the excitation of one excites the field, even though it's a virtual excitation at U2 order, and excites the other one. In that case, it's a cosine factor square.
Oh, I see. Because
the orientation between the two orbitals, right?
I see what you're saying. Well, it is different in this case, for sure.
Go ahead.
But yeah,
keep going.
So if there are no other questions, yeah, let's talk about the UDW model. So what I will call the UDW model here would be this the simplest possible particle detector model, right? It is the simplest model because it will consider the detector to be a qubit, so the simplest possible non-relativistic quantum mechanical system. The field to be a quantum scalar field, a real quantum scalar field, so the simplest possible relativistic quantum field we have. And we'll assume even that the interaction is linear in the field. So that's also going to be the simplest interaction you could conceive. That is non-trivial. And for every purpose, you could consider the detector to be a Bloch sphere that is there probing the scalar quantum field in the way that we will prescribe soon enough. Just a comment about the UDW model, right? The first person to introduce a particle detector model ever was Unruh in his review about black hole thermodynamics, or comments about black hole thermodynamics in 1876. And sorry, 1976. And then Bryce DeWitt has published in 1980 this this book here, this survey about general relativity. The simplified this UDW model, which is actually this qubit coupled to a scalar field. So that's where this whole idea of UDW model and particle detector models arose. And after that, well, there are infinitely many citations to add regarding these, but well, time is finite and so is space. So in the slides, I mean. But yeah, so yeah, so we need three ingredients, right? The detector, the quantum field, and the interaction. So the detector is a simple two-level system with the free Hamiltonian that only has the energy gap. So I assign energy 0 to the ground state, energy omega to the excited state. But we'll see that in the end, everything only depends on the difference of on the gap. So doesn't matter. And this Hamiltonian is defined in the proper frame of the detector that undergoes a trajectory z of tau in spacetime. So a time-like trajectory, of course. And so here's just, well, you can imagine that you have a Bloch sphere evolving here along spacetime, and that's pretty much it. The field will be, as I said, the simplest possible relativistic field, right? The real scalar field. It satisfies then the Klein-Gordon equation, and with the proper metric convention here. And of course, then after you pick a basis of solutions to the Klein-Gordon equation, you can expand this field in terms of these modes and promote the coefficients to creation and annihilation operators that satisfy the commutation relations, right? And just a comment: if we're willing to see the relationship between electromagnetism and this scalar theory, of course, we have to set the mass to 0. Otherwise, the properties of the field are completely different, right? When the mass is 0, then the support of the propagator, for example, is in the border of the light cone, the boundary of the light cone, and in the light cone itself, if you will. And if the mass is not 0, then there is no 0. The support of the propagator is inside the whole light cone. So in between the whole field cone. So the properties of the solutions are really different. So if you want to talk about electromagnetics and try to get analog things, you should set the mass of this field to be 0, at least to get something similar. And then the last thing we need to do is to prescribe the interaction. I will prescribe it at the level of this interaction Hamiltonian density, which once again, it's a scalar for me. If you want to get the actual Hamiltonian density, this would be the function you multiply by the dV, by the invariant, or by the square root minus g d3x, essentially, this density per se. But yeah, and here we can identify the same elements, or well, the same essential elements that we had for the atom probing the electromagnetic field. So we have, but before that, sorry, this is the only particle detector model that we'll talk about here, in which we can factor a detector monopole moment out of this interaction. So if you recall the electromagnetic one, we had a lambda effects like here and a lambda star effects in the other one, because this lambda effects was not necessarily real, right? So in this case, it's usually assumed that this mirroring function is real, so that you can factor it out and you get a detector monopole moment here. But this is the only particle detector model we'll see here where you can actually do that. In the other ones, in the fermionic, in the complex one, and even the electromagnetic one, we didn't have that. But here we do see the essential features of this particle detector model. We have this coupling constant, which is usually assumed to be small, so that we can perform perturbative expansions in this coupling constant. We do see the spacetime mirroring. In this case, it is a mirroring scalar function, right, that will control the shape and the profile of the interaction, both in time and in space. This can contain a switching function, a space mirroring function, and all of that. And at last, we have the detector proper gap, right? Properly coupled with the raising and lowering operators. And as I said before, we have interaction which is linear in the quantum field. So with this, we already can jump into the examples. We can compute the excitation probability. Nothing of this is new to anyone at this stage. So, but still, it's good to do this review. The idea is that if you have your field in a given state psi, your excitation probability will be given by this sort of Fourier transform in the proper time of the detector, evaluated at the detector gap omega of the 2-point function at the state, with the space-time mirroring function here acting as regulators for this 2-point function when needed. And again, we'll be mostly interested in one particle states here in this presentation. So let's see what happens if we consider a one particle state. This is a general one particle state for this theory. So you pick a momentum distribution and associate it to the states on each mode. And then once again, we see this very similar thing that happens in the electromagnetic case. This is a general feature of quantum field theory, which is that the Weightman function for this one particle state was split into the vacuum contribution plus a counter-rotating term plus a co-rotating term, which will be the one that will contribute in the long time limit for a inertial detector. So these two terms would vanish as well in the long time limit, and only this one would contribute, right? So in this case, if we actually try to compute things for the explicit, oh yeah, sorry, and here's again the citation to Erickson and Allison and Eduardo, where they first did these computations in flat spacetimes for an inertial detector, and they found the splitting, the only the only co-rotating terms and the two terms that vanish in the long time limit. But here we'll generalize a little bit their results. Okay. So here, at least for the case of a massive field, and it's interesting to see what happens in that case. So here, what happens is, well, we will consider again the field to be in this general one particle state with momentum profile, with momentum profile function given by this Gaussian centered at k0 with spread sigma. And the detector will simply be a point-like detector. And again, I will take the point-like limit so that this chi of t will just be taken to be 1 in the limit, right? And in this case, the probability found is this one, okay? Where, here, this is a big expression, okay? I would just like to comment on the fact that this is exactly the excitation probability obtained by Erickson, Irene, Allison, and Eduardo, except for the fact that here I have considered mass. So if you set mass equals 0, you obtain exactly what you obtained there. But here, there's this distinguished thing, which is this Heaviside theta of the detector gap minus the mass of the field. This means that in the long time limit, if your detector's gap is less than the mass of the field, your detector will be blind to the particle state. So the gap of your detector has to be large enough so that it can accommodate for a full particle of your field. And of course, this was not present in their result because in their case, mass was just 0, so this was not an issue, right? But this is the excitation probability, and I have plotted it here in 3D for 2 different values of masses and multiple various values of sigma. So first of all, we see resonance now not at omega equals k0, but at omega equals the energy that, again, it's the average energy of the particle, but it's not only k0 in this case. So it's the square root of k0 squared plus m squared, right? There's the relativistic energy of the average energy of the wave packet. And here, there's the plot for the mass equals to 0. So this plot is exactly like Erickson's one. So this is, you can again see this resonance effect at omega equals k0 because here the mass is 0. And as you decrease sigma, you see that you get this resonance effect, but the probability drops, right? The probability goes down. In this case here, I have plotted using the same scales here. So this is 2, the difference between this axis and this one, but it's centered at the resonance point. Here it's also 2. and the scales here are also the same. They go from 0 to 0.3. So it's as if the mass of the field was responsible for sharpening this peak. I have another plot later to show this explicitly, but here you can see, right, I picked this value of mass, which was the square root 3 times the energy, well, the modulus of K0. And then what we get is that here, this will just turn to 2K0, and we do see resonance at omega equals to K0 as expected, right? Which is sharp, which is more sharp. So just a comment on the fact that was seen by Erickson there is that if you localize your particle too much, so if you send the localization of the particle in momentum space to 0, so if you localize your particle in momentum space too much, what happens is that your particle gets completely delocalized in position. And because your detector is a localized system, in the end, because the average density, the energy density, or to be honest, any density related to this completely delocalized particle in position space is 0 effectively, if you take this limit, then the excitation probability will also go to 0, although the resonance effect will be more present. So you will see a peak which is more centered around the resonance, but the probability is lesser, depending as you send sigma to 0. And then just a last plot regarding this this massive case, so that we can see the effect of mass. Here are the plots for increasing mass as the plots themselves increase for sigma equals 0.1. And what happens here in this case is that, as you can see, mass really sharpens the peak. It not only increases the excitation probability, but it also makes the peak, makes this effective standard deviation here lesser, right? So these are the facts that I got regarding the scalar field, and this will be important so that we can compare these with the neutrino detection models that we will talk about later, because, well, neutrinos do have mass. Or, well, if you don't think so, then we should argue about it later. And just commenting about the overall effect, the overall comparison between these two models, right? So they're very similar if you get the UDW with the mass equals 0, okay? Even the interaction Hamiltonian densities are very similar. The only difference is that the vector nature of the field is not grasped by the scalar field, as expected, right? And then, of course, the relative angle between the dipole and the propagation vector is not present. There's no angle dependency here. But this is exactly because, well, this is a scalar field, right? There's no way that a scalar field would be able to grasp the features, the intrinsic vector features of the electromagnetic field. But in every single other aspect, they're very similar. If you shoot a particle in the electromagnetic case, you do see the probability decreasing, and everything. Overall, the two models are very similar for probing one particle states, at least in this regime that I've considered here. So would anyone like to add anything on this? Have any questions so far? Also, I'll just move into the fermionic particle detector models. And I'll take that as a no. So let's talk about the third model that we'll be talking about here. The third model that I'll be talking about here. This is the Beta Decay model, the fermionic particle detector model. And before anything, I'll just try to motivate this a little bit and try to convince you that this model sort of works. So this is a particle detector model that probes neutrinos, right? It probes the neutrino field. Technically, it probes antineutrinos more than anything, but ends up probing both. And for us here, the detector will be a nucleon, so a neutron-proton system, and the electron involved in this beta decay process. So for those of you who don't know, the beta decay process is the event when a neutron decays into a proton, electron, and neutrino. This is very well described by many different theories, as we'll see. And for us, given that we only want to probe the neutrino field, we will just take all of these three elements here and say, this is our particle detector model in a given way. And what's most important about this model here is the fact that it successfully describes neutrino oscillations, as was shown in our paper here by Bruno, Landulfo, Matzes, and I. And yeah, hopefully I'll be able to explain to you how to get to this model from a more fundamental theory. So first of all, the beta decay, right, which is this process where the neutron decays to a proton, electron, and antineutrino. This is very well described by interactions via the weak force, right? And so the standard model is very good at describing these things. I mean, should be technically quarks here decaying, but you can talk about this sort of process by using the weak force and by using the standard model. But of course, this can be simplified by means of essentially integrating out this W boson, and then you're left with an effective theory here. So this effective theory was actually described before the discovery of the weak force, and before the standard model. And this was proposed by Fermi. Essentially, Fermi proposed this a Lagrangian that would be able to describe this process. And the Lagrangian is this one, where you see the proton and the neutron, the electron, and the antineutrino. Only the left-hand part of them coupled, because, well, the weak force only couples via the left-hand component, right? And the coupling constant in this case, the constant that would be responsible for this interaction would be the Fermi, the G Fermi constant, which has dimensions of 1 over energy to the 4. And well, this would be then the effective Lagrangian for this model. And our goal now will be to get this Lagrangian and obtain a particle detector model out of it. So for that, we need to make like 2 replacements or 2 assumptions there. So the first one is that we want to move this, to change this neutron proton term to essentially to a hadronic current term. And that evolves according to the difference of mass between the neutron and the proton. And the reason for this is that, well, we will assume the neutron and the proton to be way heavier than anything else, because they are. And then it's fair to assume that they will not get much kinetic energy out of this decay or process in general. Then they will be sort of at rest with respect to the center of mass of the atom where this process occurs. Then they will only evolve with respect to their rest masses, right? And then if you plug this into the neutron and the proton, you end up getting something that looks like this, where N and P would denote states for a 2-level system that would consist of having a proton, having a neutron, and this would be the raising operator that would map a proton into a neutron, right? And the second assumption that we have to make to reduce that Fermi-Lagrangian to a localized system that interacts with the neutrino field is to replace the electron by essentially a effective electron state that plays the role in this interaction, that has this effective energy omega e, which will not only be the mass of the electron, but also this will have to contain sort of a kinetic term as well, associated to the average energy of the electrons involved in this process. And this u of x would be a spinor function that will be associated to the position profile of the electron involved in this process as well. And the AE would be the electron annihilation operator. If this would be an E bar, then this would be U bar and AE dagger, right? So if we plug these 2 things into the 4 Fermi Lagrangian, the 4 Fermi Lagrangian, then we end up with this theory here, which sort of looks like a particle detector model, because again, we have our coupling constant, we have something that can be identified with an energy gap, and we do have a sort of space-time mirroring, which is weird here. It's composed by a spinor and a vector as well, but it is coupled to a quantum field. The only thing is that we need to identify the states associated to this effective 2-level system, right? so we need to see these guys here as essentially raising operators and this guy here as a lowering operator, or vice versa, right? So it's not hard to do this. You just define the ground state to be the state that contains the one electron involved in the process with its average energy, and one proton, the one proton involved in the process, and the excited state would be the no electron state and the neutron. So if you want to talk about the decay of the neutron to the proton and electron, then this would be going from excited, which is neutron and no electron, to ground, which is one electron state and the proton associated to this process. So if you do this and you plug these into the interaction Hamiltonian, you take these under consideration, then the previous terms that we had here, this AENP and AE dagger PN, turn exactly to raising and lowering operators in this model. And then we have exactly coupling constant, energy gap, space-time smearing, and again, now we have the raising operator coupled to the neutrino field and the lowering operator coupled to the antineutrino field. So this is how to get to this interaction. The only thing is that, well, this is specifically for probing neutrinos, right? So this U would have to be a left-handed spinner in order for everything to work with the neutrino field. And well, these are effective particle detector model, right? It's a nucleus or a nucleon inside the nucleus, and it contains a sufficient amount of electrons around it so that it can undergo this this process, or no electron if you're looking for the excitation. Sorry, it has a sea of electrons if you're looking for the excitation, and no electron if you're looking for the de-excitation. But we just want the electron to be there in order that the beta decay processes can occur. And in any case, the electron, the proton, the neutron are all many times more massive than, sorry, the electron, the proton, the neutron, the electron, the proton, the neutron, yeah, are all many times more massive than the neutrinos. So it's expected that they will more or less stay at rest with respect to the emitted and absorbed neutrinos, or that they can be localized if you talk about neutrino mass scales and things like this. So in what follows, we'll consider a slight generalization of this model. We'll just allow the spinor field to be a general field, right? So let's consider a general spinor field. This can be in curved spacetimes and whatever, right? So you can always expand it in terms of solutions to Diric's equations. So this U and V, essentially, which are the positive frequency and the negative frequency modes. And here it's very important to stress that the U and the V's, they're different, okay? This will show up again when we talk about the complex model soon. And another very distinct feature of fermionic fields is that they don't satisfy commutation relations. They satisfy anti-commutation relations, right? So this is something that will also show up in the excitation probability. And most importantly, they have well, fermionic fields, complex fermionic fields at least, not Majorana fermions, they have particle and antiparticle content, right? So B's, the B's here are associated to antiparticles, and the A's are associated to particles, right? And then the particle detector model, right, will interact with this field. Here we have, again, the coupling constant, energy gap, and the space-time smearing. And I put this slide here essentially to say how this space-time smearing is complicated, in the sense that, well, in principle, it depends both on a vector smearing, right? On a vector field to smear the hadronic current, essentially, if you think of the beta decay model. And it also depends on a spinor smear. So it is way more complicated than the case in which we only had for example, the electromagnetic case, where we only had a vector field smearing for the electromagnetic field. So that's why we'll be interested in sort of reducing this particle detector model, or finding analogs to this. It is a complicated model. The field is more complicated. The detector is more complicated. Everything is more complicated. So with this, we can compute the excitation probability, right? And once again, if the field's in a state psi, it will be given by this Fourier transform of the 2-point function on the state psi. But here it's a little bit different because the order of the spinors mirroring essentially does matter a lot. Okay, the order of the spinors mirroring has to be contracted in this way, and with this 2-point function, fermionic fields actually have two different 2-point functions. If you place the psi here and here, or if you place the other way around, and this shows up in the other way around shows up in the excitation probability. I'll write it down later so we compare it. But well, this will be the excitation probability. And then if we do the standard thing we've been doing, which is to consider a general one-particle state. Sorry, I'm missing daggers here. Should be B dagger and A dagger. But if we consider general one-particle states, so they will now depend on the two spinor polarization. So R equals 1 and 2. And they will also depend on the momentum distribution. But here we see that we have the particle content and the anti-particle content, essentially, of the field. Okay, so you can create antiparticles. And a general one-particle state, in principle, is can consist of both particles and antiparticles. Again, I'm sorry for the daggers here, but yeah. And once more, we see that the 2-point function decomposes itself as the sum of three functions here. The vacuum contribution. This is the counter-rotating term in this case, and the co-rotating term is this, where this big G is associated to the antiparticle content, and the big F is associated to the particle content. So the thing is, in this case, if you consider inertial detector in Minkowski, then what will happen is that the vacuum white one will go to 0, the counter-rotating term will go to 0, and only the antiparticles will excite the detector. And this is because the process that will be considered here in terms of beta decay would be neutron plus anti-neutrino going to well, would be associated essentially with the inverse of this process that demands the anti-neutrino to be absorbed in this case, right? So okay, this means that only the antiparticles contribute in the long time limit here, right? And if we go to the, oh yeah, before going to the simple example, just a comment on the vacuum excitation and de-excitation of this model. Well, if you write down the vacuum excitation and the vacuum de-excitation, here they are, right? And you see that the position of the sidebar and side are swapped. And of course, you also have to accommodate for the fact that the mirroring functions are spinors, so you cannot just change their orders in any way. But these are the vacuum excitations and de-excitations, right? And this means that the detector breaks a symmetry present in the case of detector couples to real fields. So when you get a detector and you couple it to a real field and you change omega by minus omega, you can think that essentially you're relabeling who you're calling the excited state and who you're calling the ground state. But in this case here, you would also change whether the excitation of the detector would be coupled to the field or to the conjugate of the field. So there's the symmetry break here. Of course, this is true for the vacuum probability, but moreover, if I were to come here and talk about the excitation probability of this detector, everything that will change would be, well, omega by minus omega, and particle with antiparticle for the counter-rotating and rotating terms. So the symmetry is broken for pretty much every single state, unless you really fine-tune it. So there's this symmetry break in this model, right? And then we go to this.
Excuse me.
Go.
So isn't the symmetry restored if I just replace omega by minus omega with also the replacement of particle and antiparticle?
Yes, it is.
So this just boils down to the fact that like CPT for a real scalar field is just time reversal, but if you pretty much do anything else with more complicated fields, you have to do charge conjugation, for example, too.
Yes, essentially, yes. In the end, yes. It's because you have to also swap the roles of particles and antiparticles, and not only the energy gap of the detector. Perfect. Yeah. there's a way.
But you see, that's
putting-
important. That's exactly the intuition that needs to be fleshed out, because people working on detectors, right, are going to be, oh, hold on. You're breaking a symmetry that you shouldn't be breaking, perhaps. You know, I mean, this is exactly one of the key points, actually, Bruno. Yeah, being able to
No,
explain.
because-
this is a very good way of putting it. Yeah.
Because changing omega to minus omega can be seen as just time reversal. Well, so then so the fundamental symmetry is CPT, not time reversal. So it's fine to break.
Yeah, in a way, right? In a way,
This
because
is
it's
a
time
good way of-
reversal only in the detector gap kind of thing, the dynamic of the detector. So for that system in particular, it's time reversal.
Yeah,
Like,
it's a
time reversal in the
particular
interaction.
yeah, it's a particular instance of that. But I think it's good to have that clear. You know, yeah.
No, yeah, thanks for putting this in this one. Yeah, for sure, in these terms. Okay, yeah, so going for the analog simple example, in order to compare with everything else that we had from before, let's assume the field to be in this state given by a general one particle state, right, with particles and antiparticles, both centered at momentum k0. Now you see, I have to actually pick here 4 scalars to choose the essentially the effective probability of having particle with polarization 1, particle with polarization 2, antiparticle with polarization 1, and antiparticle with polarization 2, right? So these are the 4 numbers, alpha 1, alpha 2, beta 1, beta 2, okay? So they will show up later. And the detector, the thing is, I want the detector to be pointline. So this hadronic current will simply be a Dirac delta, right? In the long time limit, there will be no switching function anywhere. And this u mu will be simply the force velocity of the detector, right? And then whatever I pick for this spinor smearing function, whatever sort of spatial dependence it might have or anything like this, will be completely washed out by the product with the Dirac delta function here in the for density, in the for current, right, in the hadronic current. So it really doesn't matter, or just write this as A1, A2, B1, B2. So this is again the particle contribution in the Dirac basis. There's the antiparticle contribution in the Dirac basis, and let's see what shows up here. So the probability actually reads this expression here, right? So again, we see this exponential that was also present in the scalar case, and we do see this term here, which only looks at the antiparticle. This is essentially the scalar product between the antiparticle component of the field state and the antiparticle component of the spinor smearing function for the field, for the detector, sorry. So this is essentially the inner product between the antiparticle content of both of them. As I mentioned previously, only the antiparticle content actually matters in this case, and the long time limit and inertial detectors. So that's why we see this, again, only the antiparticle content. And actually, if you are to compare this with the scalar, the real scalar even, in 3D, look at this. This is the probability for a real scalar in 3D. So, I don't know how you call it in English, jogo dos sete erros. It's a spot the difference, maybe. It's very little, right? I mean, you see this omega plus m here, which is not present here. The units of the coupling constant are different. The units of this gamma, gamma has to come with units out of the fact that B1 and B2 are components of a spinor. But other than these two, everything is the same, even the factor of square root pi, right? And of course, there's this mass dependence here, which tends to increase even more the probability with mass, but that is pretty much it. And the fact that it filters down only the particle content of the field, right? So these would be the major differences between the scalar one and the fermionic one. I didn't even bother plotting this because it's exactly the same plots that we had, except for this factor here that really influences very little the shape of the plot. So this means that once again, we have resonance at omega equals square root of k0 squared plus m squared, and everything else works exactly like the massive scalar case, but filtering out only the antiparticle content of the state of the field. Now, finally, let's try to reduce this model to this complex UDW model. So yeah, we're essentially looking for a model that is able to describe features of the fermionic field, right? Up to some extent, of course, won't be able to press spin or things like this. And we also want a model that is simpler than this fermionic detector and that measures antiparticles. So, I mean, the only thing that's simpler than a spin half particle that has antiparticles is a complex scalar field, right? So we'll be focusing on that. So we'll consider a field to be a complex scalar field here, right? So it can be decomposed in terms of the positive and negative frequency modes. But here notice that these modes here, one is the conjugate of the other, unlike in the Dirac case. And this will show up later, okay? And also, I will not impose either commutation or anti-commutation relations. I will leave this free. Although commutation relations are more can be seen as more fundamental, right? Although anti-commutation relations for scalar fields can be argued to be less physical, I'll just leave it there and let's see what shows up out of this model. Okay. But well, this is the composition of the fields. And then we only need to find a way of reducing this interaction Hamiltonian density that we had for a spinor field to a complex scalar. So let's see what we have to change. So first of all, the units of the coupling constant would have to change, right? This is the interaction Hamiltonian for the fermionic one, right? So what do we have to change in order to adapt it to a complex scalar version? So the units must change, for sure. There's no reason to change the gap or the sigma plus. The detector will still be a two-level system in this description. Of course, we will have to change the sign sidebar by complex fields, right? So instead of sidebar, we should have a side dagger, right? Because side dagger is the one associated to the creation of particles, and so is sidebar. And finally, this space-time smearing function should just be instead of the spinor vector, whatever we had before, it should just be a simple complex scalar function, right? So applying these changes, we get this interaction Hamiltonian density here. So you can see here only the side dagger and the lambda of x. So this will be so let's go term by term. The coupling constant is there, the energy gap is there, and and the space-time smearing is here. Now, just a maybe complex. You have, well, you can allow it to be complex. You can, it's your choice whether you want to allow the space-time smearing function to be a complex function or not. But why not in this case, right? We're coupling it to a complex field, so let's do this. But it's very important to notice here that even in the case that the space-time smearing function is real, you cannot factor this as a monopole of the detector interacting with a complex field, right? Because the de-excitation part couples to psi, and the excitation part couples with psi dagger. So just keep in mind that, again, we cannot factor out a detector monopole moment coupling to something. Just like in the electromagnetic case, just like in the fermionic case, and unlike in the UDW. But yeah, also nothing prevents us from going back to the UDW model and allowing this space-time smearing function to be complex. But yeah, then the excitation probability for the field in a given state psi will once again be given by the Fourier transform of the white one function at that state smeared by the space-time smearing functions lambda, evaluated at omega, this Fourier transform with respect to the proper time of the detector. And if we go to our one particle state once more, then here our general one particle state will be a particle and anti-particle content. And the excitation probability will once more factor as the vacuum contribution, a co-rotating term that will contribute even the long time limit for inertial detectors, and a counter-rotating term, which will not contribute in the long time limit for inertial detectors. So here you see this plus or minus. This comes out of the either commutation or anti-commutation relations that I can put for the fermionic field. So this means essentially that if you impose commutation relations for your field, the particles, they help out with the excitation probability. This is always a positive term. And if you don't, then they actually decrease the vacuum excitation probability. If you impose anti-commutation relations for your complex field, then the particles would diminish the vacuum excitation probability, right? And once again, the big G is associated to the antiparticles, big F is associated to the particle content of the field. So if you want to reproduce up to some extent without spin, the excitation probability, at least, of the fermionic detectors, you should impose anti-commutation relations for your complex field psi, which is expected, right? You should, at the very least, impose that your field associated to this particle detector model should satisfy the same commutation or the same statistics that the field that you want this to be similar to satisfies. And now, just a comment on the vacuum, excitation, de-excitation. Although the excitation, de-excitation probabilities will not be symmetric by this exchange of omega by minus omega here in general, because you will swap the roles of F and G anyways here. What's going to happen is that for complex fields, due to the fact that the positive and negative frequency modes here are related simply by conjugation, the vacuum Whiteman functions, no matter the order that you put here, are the same. And this means that this detector model will preserve the vacuum omega to minus omega symmetry. Only the vacuum one, but not the other ones in general. Okay, so this is an interesting feature of the fermionic field that is not grasped by this complex scalar model, right? And with this, we can finally go for a last example, which is the same one as usual, but with a complex field. So here we'll pick our general one particle state, consider a Gaussian momentum profile distribution here for the particles and for the antiparticles with spread sigma. Consider detector to be point-like in the long time limit. So this chi of t will actually be 1 for this computation. And what we get, surprise, surprise, is exactly the real case multiplied by this beta factor, which is exactly the component of the antiparticle state. So, well, of course, this is the same because the Whiteman function is the same, right? That's why I said surprise, surprise. Also, you have zero excitation probability for the gap of the detector less than the mass in this long time limit. And this is exactly the real probability times beta squared, which means in particular that this mimics very well the fermionic particle detector model, even with the filtering of the antiparticle content of the state of the field, right? Which is one of the features that the scalar model could not grasp, right? So with this, this is the last example I wanted to show, and we already can present some conclusions regarding what I have shown you here. So first of all, let's start with the qualities of this complex detector model when trying to probe particles or antiparticles, right? So it is able to distinguish particles from antiparticles, right? And this is a feature of the fermionic field that is grasped by this complex particle detector. It gives the approximate excitation probability for the fermionic detector in this point-like and long time limits. But also, I would expect this to be true for the non-point-like limits as well, and also for I mean, I don't know if for short interactions, but for sure for long interactions that are not infinitely long. Now, the things that are not grasped by this detector is the fact that it doesn't break the omega to minus omega symmetry in the vacuum, while the fermionic one does. And this complex detector is not able to grasp the spin degrees of freedom, of course, the polarization ones and all of this part. But once again, this is expected, right? So in the end, the final conclusion is that the approximation that the light matter interaction by the scalar DW model is better than the approximation of this fermionic particle detector by this complex one. But the only major difference that arises that I was able to spot so far is the fact that the complex particle detector, this complex UDW model, does not break the vacuum probability, the omega to minus omega symmetry for the vacuum probability. And that's it. This is what I have been doing with Edu.
Nice.
Sorry for the long presentation. It was super long, right? It was like
it was a really good presentation, Thales, really good. This is how slides should be. You know, this is like an example of how slides should be. You have seen in the conference some slides that were more loaded than others. This is a very simple, very not loaded, clear ideas in every slide. I really enjoyed that.
No, thank you. Thanks for that.
Anyway, questions, people?
Yeah, I'd like to have feedback from everyone, please. We're in the process of writing and correcting things, so any feedback is very, very well appreciated.
I just have one comment. Since your calculations in this presentation are way harder than what I did in the other paper, right? Actually, you can just do the short time limit. I managed to do it like in closed form. So if you are kind of masochistic, I'm damn sure.
Erickson, that's unfair. In level of difficulty, they're extremely similar. They're actually the same integrals, kind of.
No. By
Not for the electric field, but for the rest, I'm pretty sure. Yeah.
I mean, yeah. It up to your interpretation of what's difficult. I'm including the fact that it's more tedious. So that's one thing.
Yeah, it is more tedious with more terms.
I mean, the quadratic coupling, sure, is certainly way harder, but I mean that's a separate thing. But I just want to say that for real scalar field, the closed form expression for the short time, like the Gaussian interaction for Gaussian switching time, right, is also readily available. So you can just try it if you're kind of masochistic. But yeah.
Oh no, yeah, I'm pretty sure that it can be done. I could do it, but is there much?
I don't think you gain anything, which is why I didn't try to care too much about that thing.
I would bet that the fermionic one gets much more complicated in the long time limit. The fermionic one would get, out of what I remember, because
yeah, it might affect what gets washed out first and how fast things get washed out. But apart from that, I don't think the overall picture will change.
I was about to say, short time behavior is nice because short time behavior is where the interesting stuff happens often. But this is different scope, right? In a way, this is more.
Yeah, it's like you're trying to answer different questions. I guess that's the main thing. Yeah.
When we finish recording, by the way, I'll share something that is related to this.
Okay.
But after the recording is done.
So any other questions? Any comments? Adan, can you do quantum field thermodynamics with complex fields?
Adan can do anything. It's great.
Well, I guess that's it then. You can stop the recording and share the thing.
I think, to be honest, the lack of questions, I think, responds more to you being really clear. And people really being very knowledgeable about the background, I think, than anything else. It was great. Yeah. Okay, I'm gonna stop recording now.